All right, hello everyone, welcome back. All right, we're gonna pick up 6.6. We're gonna try and wrap up the improper integrals. So last time what we saw were the type 1 improper integrals where you're trying to find the area below a curve on an infinite interval, either from a to infinity or from negative infinity to b or from negative infinity to infinity. And so if you did your homework, you saw that there were, different times where you would have to apply a limit and perhaps use L'Hopital's rule if necessary. Were there any questions over anything?
I didn't get that far on the homework.
Okay. You mean you did some but didn't get that far, or you just haven't had an opportunity yet?
No, I just did until problem 11.
Okay. Were those okay?
Mm-hmm.
Okay.
Yeah, they were pretty straightforward.
Okay.
I have a question. So in the homework assignment on your videos, you were only going towards with the odd. How can I get the answers for the even?
Well, you could come to my office hours and I could help you out with those or tell you the answers. I'm not going to post the answers for the evens. That's normally professors like to only do the odds and not publish even answers because there are a lot of professors that use the evens for tests. So I don't want to be the one who publishes even answers,
Okay.
What I do is I go to Google and I type in integral calculator, and there's a website there that comes out at the top that gives you all the steps and everything for free.
The problem is I use those ones, but then at times if I'm not getting the same answer, I look at the steps and they're using other methods to calculate those answers.
Yeah, that's the only thing, is that sometimes they can vary by the methods that they use, and some of their algebra can get pretty intense.
I think the best approach is just to do the evens, and if you do the evens right, then the odd, either 10 or 11 or 12 and 13, they're close, they're similar, but not exactly the same. So if you do
because I've just been doing the odds, and I think pretty much it helps me out.
Okay, well, come to my office hours. We can discuss even problems all day long. All right, so type 2 improper integrals have nothing to do with the interval being the problem. It is the integral that is the problem. The integrand itself, the function you're integrating, has a discontinuity on the interval that you're looking at. So for example, if we take a function or we take this integral, let's say we want to go from -1 to 1 of 1 over x dx, then well, you know what? Let's make it go from 0 to 1. Let's start out here. If we go from 0 to 1, we notice that the function itself, the thing we're integrating, f of x, that's 1 over x. Well, f of 0 is undefined. And therefore, if we're trying to think about the area there, the graph of this function looks like this. At least to the right of the y-axis, it looks like this. Last class, we were saying, hey, what happens if we start at 1 and we go try and find that area? But now this question is saying, no, don't look to the right of 1. Look between 0 and 1 and try and find this area. But you can see we have a similar issue. It's infinite up here. We've got area as that function asymptotically approaches infinity as we approach 0 from the right-hand side. So we still have a similar concept here. Do y'all see that? It's very similar to what we've done before. But how do we go about doing it, right? We know that for the type 1, we just set up a limit, right? And that's what we did. We just set up a limit. We let that limit of integration go to infinity or negative infinity or something like that. So here's the way we're going to do this. we're going to realize that the interval that we're integrating over is the interval from 0 to 1. I'm going to highlight or circle the 0, however you want to do it. You need to understand that right here we have a discontinuity. I'm just going to put discontinuous like that. And so what we want to do is pick a point to the left, to the right of that, let's call it A. As long as this A is to the right of 0, then we should be okay, right? Like if we pick 0.1, let's say. So if I did the integral from 0.1 to 1 of this function, I'd be in business, right? I could do that. I could go, instead of 0.1, I could go 0.01, or I could go 0.001. So why don't we just, instead of doing that, why don't we just call this, I don't know, t, right? And then take the limit as t approaches what?
0.
0. Now, from which side? This is important. From which side are we approaching 0? Left side or right side?
From negative to positive?
Look at your interval, right? Here's your interval. You're going between 0 and 1, right? We picked an A here. That A was to the right of 0, wasn't it?
Mm-hmm.
So we want to be approaching that 0 from the right. Very important right here that you understand that this limit, we're going to approach 0 from the right. So I put a little plus sign up on the top right-hand corner of the 0. So this is back in Cal 1 what we refer to as a one-sided limit. Okay? So this is now going to become, I'm just going to rewrite everything. The limit as t approaches 0 from the right of the integral from t to 1 of 1 over x dx. Now, before we do this, do y'all remember what the answer was from last class when we went from 1 to infinity of 1 over x? Do you remember what that was?
Converge
or diverge?
Convergent. Converge, right? Divergent is when there's a number.
There is a number. There's a number 1 right there.
It diverges if it's less than 1?
Less than or equal to 1. Less than or, so if the power on that x is less than or equal to 1, it diverges. Okay, we did talk about that last class somewhere. Wait, oh, here we go. There we go, right there. The integral from 1 to infinity of 1 over x to the p dx will be equal to, well, if p is less than or equal to 1, it will diverge. All right, that's from last class. So that's what happens if we go from 1 to infinity. What do y'all think if we go from 0 to 1? You think we're going to have divergence or convergence? I don't know, right? Let's see. Let's see what happens. So we're going to do this the same way we've been doing things. We're going to do the limit. T is going to approach 0 from the right. Okay, we need to find the antiderivative of this. We already know the antiderivative that's going to be natural log of x. I'm not putting the absolute value because I'm to the right of 0, so I know I'm plugging in positive values. T to 1. Now limit t approaches 0 from the right of, okay, I'm going to plug in the two things now. Okay, plug in 1 first, natural log 1, and then we plug in natural log of t. And let's see, limit, well, I guess right now we can do this, right? The natural log of 1 is 0 minus, now what we're doing is taking the limit as t approaches 0 from the right of natural log of t. Where is that headed?
Infinity.
Negative infinity, right? So that goes back to, you have to understand what the natural log function looks like. Here's what natural log looks like. But now we're headed towards 0 from the right. So as you are on this function, here's my little man, he's walking along the function, approaching 0, here's 0, he's approaching 0 from the right, the function is dropping him down to negative infinity. So this is headed to negative infinity. And so negative infinity is going to be positive infinity. So what does this integral do?
Diverges.
It diverges. It diverges. Okay, well, let's do another one. Let's do the integral from 0 to 1 again. This time, let's do 1 over x squared. Now, do y'all remember what that did last class when we went 1 to infinity?
Converges.
That converged, right? That converged, but this one goes from 0 to 1. So let's see. It seems like it should converge. Let's see what happens. Okay, so first thing I'm going to do. Okay, so watch what I'm doing. I'm going to draw a number line. Here's my interval, 0 to 1. I'm going to highlight or circle the fact that 0 is where I have a problem, right? This function is undefined at 0. So I'm going to have to approach 0 from the right-hand side, just like we did the last one. So I'm going to go limit, t is going to approach 0 from the right, integral t to 1 over x squared dx, which should be equal to the limit t approaches 0 from the right. Okay, antiderivative. So we've done this antiderivative many times. I'm just going to get straight to what it is. The antiderivative of 1 over x squared is the same as the antiderivative of x to the negative 2. And then you use your power rule. And then I just rewrote it as negative 1 over x squared. Now limit t goes to 0 from the right. Okay, we're going to plug in two things here.
How do we know that 0 is going from the right?
Because the interval, look at your interval on the integral that's given to you. You're going from 0 to 1, right? So you're not allowed to be on the other side of 0. You have to be from 0 to the right. That makes sense? Had the original integral been this, see, that's different because now we're still undefined at 0. 0 is part of our interval, but now we're looking at an interval that goes from -1 to 0. Our problem is at 0, and so we would have to approach 0 from the left. Does that make sense? Because your interval is different. So that's a different problem though, right? All right, so I plugged 1 in, I got that. I plug in t. When I plug in t, I get -1 over t. And now what happens? See, this becomes just -1 minus, okay, let's talk about this. What is the limit as t approaches 0 from the right of -1 over t? So what I think, at least, you know, what I teach my students is to, you know, take this limit. The top is -1, right? So the top is a fixed negative number. I put a little minus sign there to stress the fact that it is a fixed negative number over, now where's the bottom headed?
Infinity? No, 1.
No, the bottom, just the bottom. T is headed to 0, right? It's headed to 0, but it's always going to be little positive numbers because you're to the right of 0. Do you agree?
Mm-hmm. Mm-hmm.
So what happens whenever you have a fixed number on top divided by something that goes to 0? I'm actually testing my Cal 1 students on this week. If you ever have a fixed number on top and the bottom goes to 0, the outcome of this is either going to be infinity, negative infinity, or the limit does not exist. Those are the only 3 possible outcomes when you have a fixed number over 0. For us, we actually know that the top is fixed in negative. We know that the bottom is approaching 0, but always positive. So a negative divided by a positive will always be negative. So that means that for us in this problem, it would have to be negative infinity. So we're going to negative infinity here. So you get -1 plus infinity. So this thing is headed to infinity, which means it diverges.
How would you know if the fixed number over 0 is D and E?
So usually that happens, you get the DNE when your limit is from both sides. So like when you come in from one side, you might be getting a 0 on the bottom that's positive, but when you come in from the other side, you get a 0 that approaching 0 through negative numbers. So on one side, you're getting positive infinity, the other side, you're getting negative infinity. And so because they're going different places, it would be does not exist. So usually we'll only get does not exist when you have a two-sided limit where you have to check both sides. But because these are one-sided limits, we're usually going to get either infinity or negative infinity. Does that answer your question, CJ?
Yes, it does.
Okay. So this did not do what 1 over x squared did, right? As we went from 1 to infinity last class, it converged. But when we went from 0 to 1, it diverged. So it's not behaving exactly the way that it did last class. Okay, let's talk about one more of these. What if we went from 0 to 1 of 1 over root x dx? Now from last class, if we went from 1 to infinity of this, would that have converged or diverged?
Diverged.
Diverged, because this is really 1 over x to the 1/2, and that power 1/2 is less than 1, and so we would have divergence. That's from last class. So let's see if the integral from 0 to 1 diverges or converges. Well, same thing, we have a number line. Here's 0, here's 1. 0 is where we have the problem. We're going to have to approach 0 from the right. So I'll set up a limit as t approaches 0 from the right of the integral from t to 1 of 1 over the square root of x dx, which is limit t approaches 0 from the right. Okay, the antiderivative of this. So remember, that's x to the negative 1/2. So you do your power rule, and you should get, yep, 2 root x, which is same as 2x to the 1/2. You can double check that. If you take derivative of that, you should get the other one. So that's just power rule, t to 1. Any questions? Plug in 1, plug in t. And now let t go to 0. That goes to 0. The square root of 0 is 0, right? So this thing goes away, and all you're left with is 2, which means it converges.
So is it like the opposite if it diverges?
It is almost the opposite. Watch, this is what we wind up getting. The integral from 0 to 1 of 1 over x to the p dx will be equal to convergence if x is less than 1, and divergence if x is greater than or equal to 1. So that is the opposite of the other one, except that the for the equal one, it diverges both directions. So 1 over x, that function 1 over x diverges whether or not you go from 1 to infinity or 0 to 1. But the others do the opposite of what the other ones did, if that makes sense.
It does.
Okay. All right, let's look at another one here. Ready? Okay. So, do y'all see the issue?
Yeah, the limit, there's one, minus -1 and 3, right? Either cancels on one side or the other.
What do you mean?
No, the
It's
limit.
linear over linear.
No, but if x is equal to 3, that's within the limits.
So we have a problem at 3, don't we?
Yeah.
There's a problem at 3, and 3 is in our interval, right? And so that's an issue. You know what? Let's do this problem after. Let's just change it. Let's just make that a 1 up there, okay? Just so we don't get too bogged down on the integration. That right there, we still have a problem at 3, don't we? Okay. Now, let's just, don't write this down, but just imagine these limits of integration weren't here, right? Then all of you, because y'all did so well on the last test, would just be able to tell me that that's just the natural log of the absolute value of x minus 3 plus c, and you'd be happy, right? Because that's constant over linear, and you'd be happy, right? Now, that's not what we have. We have limits of integration. And I'm going from 0 to 5. Because 0 to 5 includes that number 3, we cannot just do the antiderivative. You are not allowed, okay? This would be a huge mistake to do this and then plug in 5 and then plug in 0. See what we get. We get natural log of 2 minus natural log of 3, which would be, well, that's it. Natural log of 2. You could rewrite that as 2/3 if you wanted to, using properties of logs. But do y'all see what I did? I just took the antiderivative at the 2 endpoints. I plugged in 5. I plugged in 0. I took absolute values. There's my answer, right? And this would be absolutely wrong. Okay, because you have overlooked the fact that at 3, you've got an issue. So now we have this extra thing we have to pay attention to, right? So let me rewrite the problem down here.
But isn't the 1 part of the interval too?
1?
Yes.
One
No, the
like
problem's 3.
1
So
is
we're gonna have to treat, I guess, the number 3 as our limit, attack it from one side and the other?
both sides. Yeah, both sides. So here's what I would do. I would write down the interval that we're going to be going over, 0 to 5. I would identify where you have a problem. So we have a problem at 3, don't we? So that means I'm going to have to split this into 2 integrals. The first integral, I'm going to have to approach the 3 from the left. And the second integral, I'm going to have to approach the 3 from the right. Okay, so watch how I do it. Integral from 0 to 3 of this plus the integral from 3 to 5 of this. Does that make sense so far?
My question is, how do we know that there's a problem at -3?
At positive 3?
At 3.
By just looking at the function and figuring out what makes it undefined. So you have to realize that plugging 3 into this function gives you division by 0.
Oh, okay.
Right? So you're looking for discontinuities in the function.
Okay.
Or you're looking for whatever makes the denominator 0. All right. Okay, so now each of those have their own issues. This one, the 3's here. This one, the 3's here. So let's do the one on the left first. I'm going to turn the one on the left into the limit as t approaches 3 from which side?
Left.
So if
Left.
you need to make a little number line here, here's 0, here's 3, we're approaching it from the left. I heard someone say that, from the left, right? Correct? So I need to put a little negative there. Integral 0 to t of 1 over x minus 3 dx. So that's my first integral. My second integral is a different limit. I'm going to use r. As r approaches 3, which way are we going to be approaching that one?
From the right.
From the right. And that's because now we're dealing, this integral deals with that interval and this integral deals with that interval. So we're approaching 3 from the right this time. Integral r to 5, 1 over x minus 3 dx. Any questions on that? Okay, we need the antiderivative. So limit t approaches 3 from the left. Okay, the antiderivative of that we already said is natural log of the absolute value of x minus 3 evaluated from 0 to t, and then plus the limit as r approaches 3 from the right of natural log of the absolute value of x minus 3 evaluated from r to 5, which equals the limit as t approaches 3 from the left. Okay, now I get to plug in two things here. So first I plug in t, natural log absolute value of t minus 3. And then I plug in 0, natural log of 0 minus 3, absolute value. Let me do the other one. Limit r approaches 3 from the right. Plug in. I'm running out of room here. So we plug in 5 first, natural log absolute value of 5 minus 3. We plug in r, natural log of absolute value of r minus 3. Okay, let's do it. We are going to take the limit as t approaches 3 from the left, and we're going to plug that in right there. So what happens if I replace that t with 3? 3 minus 3 is headed towards 0, isn't it? And so what this really is looking like is it's headed towards natural log of the absolute value of 0. Well, what's the natural log of 0?
1.
No, natural log of 1 is 0.
Oh.
But the natural, so you have to go back to the graph again, right? What does natural log look like? So at 0, you have a vertical asymptote, don't you? But see, this is a limit. What's happening as this thing inside here is approaching 0? Where's this natural log headed?
Negative infinity.
It's headed to negative infinity. Look at the graph. It's headed towards negative infinity. Because you're trying to figure out what happens as the thing inside the natural log gets really close to 0. Now, the absolute value here saves us because we can be guaranteed we're plugging a positive number into the natural log because there's an absolute value around it. Now, what about this? So remember I said that to be convergent, you need everything to converge. But if one of these diverge, we're done, right? We can't say we're done yet because we need to make sure that this piece doesn't go to infinity. Because just think about it. What if that there went to negative infinity? Then we would have minus negative infinity. So this would be negative infinity plus infinity, and that is an indeterminate form. Negative infinity plus infinity is like 0 over 0. So you would still need to work. Now, fortunately for us, that's not what happens in this problem. What happens here is that goes to, well, natural log of 3. and those together go to infinity, negative infinity. So we can say now, it doesn't matter. Who cares what that one does? Who cares? Because this one is going to be divergent. So the whole thing diverges. What do you think? This example was to illustrate that, number one, you have to pay attention to the interval, okay? And make sure that you don't have any discontinuities at the endpoints or within the interval, all right? If you have a discontinuity inside the interval, you have to break it into two integrals. Man, I'm sorry, grol and vol sound the same, right? You have to break it into two integrals and then do two different limits and, you know, see what happens.
So what will happen if instead of the 1, we have a 0?
Where?
On the limit. We have 1 over x minus 1 over x minus 3. What if it's a 0? Or if it's another variable? How would that complicate
I'm not sure what you mean.
So you have that integral 1 over x minus 3. What if we have, Colin, instead of having a number, a constant, what if we have another variable?
Oh, like I did just a second ago?
Yes.
Like
Is that going to, I guess I don't, so instead of having a constant, we have a variable that will also limit, right?
Well, let's see. I think this is the problem that I started with. Maybe not. It was x plus 1?
Or just leaving x alone up there.
Let's do that one. That was the first one I put up. Okay. Do we still have a problem at 3? Yes. That's the only place we have a problem. Now, we do not have a problem at -1 because it's okay for a numerator to be 0. It's just not okay for a denominator to be 0.
Okay.
So it has nothing to do with the fact, like if you're thinking, oh, -1 is a problem, it's not. It's not a problem. But
so we will not say that at -1, the limit does not exist, or it's undefined.
Nope. It's 0 at -1. The function is 0 at -1.
Okay.
So I would look at my interval. I go from 0 to 5.
Is it because -1 is not in our interval?
It has nothing to do with the fact that it's not in our interval. It is not in our interval. It's not, I agree, but that has nothing to do with the fact that I'm not looking at it. I'm not looking at -1 because I don't care about -1. It's not making my function undefined. The only thing making my function undefined is 3.
Okay.
But if we had it, if the limits were different, call it from -10 to infinity, then we will have a problem on both, right? No, just on at 3.
If let's just say we went from -5 to 5, I'm still only concerned about 3.
Okay.
I think it's easier if you look at it like a fraction. So like 1 over 0 is undefined, and that's just undefined, but 0 over 1 is actually 0.
That's right. 0, so you can have 0 on top. As long as the bottom's not 0 at the same time. It's okay to have 0 on top because 0 over any number is going to be 0, but you cannot have 0 on the bottom because division by 0 is undefined.
Okay.
Always. Okay, so this problem is just like the previous one. We'd have to split this up into 2 integrals. We'd have to go from 0 to 3 first. And then we'd have to go from 3 to 5. On the first integral, we would have to change that to a limit as t approached 3 from the left, because we're dealing with that piece first on this first integral. So t to 3, x plus 1 over x minus 3 dx. The second limit, use a different letter, r approaches 3, this time from the right, because we're dealing with this piece. And that's going to go interval, let's see, integral r to 5, x plus 1 over x minus 3. And now here's where we see the main difference between these two problems. And that is the antiderivative. The antiderivative of the last one was constant over linear. And so we were able to do it without any work. Here, we have to possibly go to the side and figure out what the antiderivative of this is. So how would you do that?
I would break it, but there's another way. Like, it's easier for me to break these two in separate. But linear over linear, I believe, was substitution.
No, we can divide, no?
What do you mean divide?
That is the same as having the integral of 1 over x minus 3. Split the integral.
So do two different integrals?
Yeah.
You could do that.
That's possible, right?
Yeah, one of them though would be x over x minus 3, which you still have to deal with that. I see two different ways. I see, look, this is a rational function. It's a polynomial over a polynomial. So you have to start with long division.
Mm-hmm.
So you go 1, 1 there, x minus 3, change the signs, minus, plus, add down, you get 4. So you get a remainder of 4 over x minus 3. So this becomes an integral of 1 plus 4 over x minus 3. And then the antiderivative of that is x plus natural log of x minus 3 plus c. I forgot my 4. Okay, we've done this, yes? Another more clever way of doing it is you could just rewrite it as x minus 3 plus 4 over x minus 3. So like that's being real clever. That's like, oh, okay, I see that if the top was x minus 3, they would just like cancel. So I make the top minus 3 plus 1, which basically turns into this. And then I split it right here. I do this over that, which is 1. And then I do that over the bottom again, and that's that one. It's just, you're just jumping around the long division that way. But either way, you should get to that. And so that's our antiderivative.
Even if you divide them into two different integrals, like x over x minus 3 plus 1 over x minus 3, will get the same answer.
Well, yeah, but my only issue here is that, you know, like, how are you going to do that one? How are you going to do the x over x minus 3?
Now I would turn to
you see what I'm saying? You're going to wind up doing long division now, or you're going to wind up doing some substitution or something, but it's more steps than just going straight to the long division from the beginning.
Yeah.
So I'm not going to work the rest of this problem out. That just shows you that there's, you know, the difference between these two is only in the antiderivative itself is a little more difficult. Let's do this one. Starting to look like test problems now.
I would try to break the denominator.
We can complete the square.
You can just factor it.
Or
Can we just factor it?
Yeah,
is that
negative
factor?
5 and 2.
So you have to, okay, so when you look at the big picture of things now, right? This is a definite integral, right? We spent a lot of time doing indefinite integrals where we got plus c, plus c. Then we talked about definite integrals where you plug in two numbers. This looks like a definite integral. What's hiding from you is the fact that it's an improper integral. That's hidden here. The only way to know this is an improper integral is to actually factor the denominator first. So you have to factor. The bottom becomes, I heard someone say x minus 5, x plus 2, right? And there it reveals itself to you. See, we're looking at the interval from 0 to 10, and we actually have a problem at 5. We also have a problem at -2, but it's not in our interval, so we don't need to worry about it. Had this gone from -10 to 10, then we would have to actually break this into 4 integrals. I wouldn't give you something like that, but I'm just telling you like that's what would happen. So we're going to do 2 integrals. One of them is going to be us approaching 5 from the left, and the other one's going to be approaching 5 from the right. Right? Okay, let's do it. Blah, 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 blah. What am I doing? Okay, so I'm going to do the integral from 0 to 5 of 5 over, I'm going to keep it factored. And then I'm going to go from 5 to 10. The first one, I'm going to do a limit. I'll use t. I'm going to approach 5 from the left because I'm doing that one. Integral 0 to t 5 over x minus 5 times x plus 2 dx. The second one, oh, let's call on somebody. It's been so long and you all just look lonely. How about Brian Vasquez? Brian?
I'm here, sir. Would it be the integral of r to 10?
Okay, what's the limit?
Oh, I'm sorry. The limit as r approaches 5 from the right.
Good. And then you said r to 10. Good. And then it's just everything else, right?
Yes, sir.
Okay, good. All right. Now, the next step is to find the antiderivative, right? So, Aisha, are you around? I don't see Aisha here. Sydney? Sydney, are you with me?
Yep.
Any ideas on how you would find the antiderivative of that?
My guess would probably be separate. I guess multiplying, separating by multiplying like 5 over x minus 5 and x plus 2, and then.
Can you separate them like that?
Imagine if you.
Can you do 5 over this and 5 over that?
I imagine you have to do like 5 over x minus 5 or 5 over x plus 2 and then 1 over the other.
Okay, yes, but it would have to be multiplication between the two still.
True.
Like if you did 5 over x minus 5, you'd have to have times 1 over x minus 2. It could not be addition or subtraction, which would mean you can't split this into 2. I know you know how to do it.
I know. I'm trying to figure out how.
So when you go back up here, you have a linear over a quadratic, right?
Right.
The quadratic is reducible, factorable. We did this on the last test.
Partial fractions?
Partial fraction decomposition. Yeah, we're going to have to do partial fractions. So we have to do 5 over x minus 5 times x plus 2 equals a over x minus 5. See, Sydney, what we're gonna get it to split into 2. We are gonna do that, but we have to go through partial fractions to do that. And then you clear the denominators. So Sydney, does that seem more reasonable now to do that? Okay. All right, so now we would go either the short way or the long way. It's kind of up to you here. I'm gonna go the short way. I'm gonna let x be 5. If I do that, I get 5 equals 7a.
Yeah, I don't think this was like on the test. On the test, I think it was more difficult.
Yeah, they were harder problems on the test. Let x equal -2 next. So you get 5 equals -7.
You can give us this problem on the final.
I can?
Yeah.
Thank you.
As a bonus point, I guess.
All right, so at this point, I think you get the idea of what would happen now. We have the antiderivative, or well, we don't have the antiderivative. So this new integral becomes integral of -5/7 over x minus 5, and then plus 5/7. Oh wait, I messed that up. That's b, not a. 5/7 over that, and then I have -5/7 over this. Now we can do the antiderivative. So 5/7 natural log absolute value of x minus 5 minus 5/7 natural log of x plus 2. Any questions there? I'm going to try and come back up here. Limit t approaches 5 from the left. The antiderivative is all of that, 5/7 natural log of x minus 5 minus 5/7 natural log of x plus 2. We're going to evaluate that from 0 to t. And then we have plus, and then we have to do the same thing for this one, right? The antiderivative in there. I'm not going to do it because I want you all to see right now, this one's going to diverge. See if you agree with me or not. Does this one diverge? Just think about what happens if you take the limit as t approaches 5 and you put it right in here.
The 0.
You'll get natural log of 0.
Yes, and
towards negative infinity.
Negative infinity.
So I can already tell. Now I'm trimming down the work here because I need to get through problems today. I would expect that you would work this out, but I can tell you right now that's going to go to infinity, negative infinity, and so this whole thing is going to diverge.
And what was the reasoning again? You said if x was 5, then natural log of 0 would be infinitive?
Well, natural log of 0 is undefined, but in the limit, as we approach 0, it's headed to negative infinity.
Okay. So natural.
What about when you said that you should always check the other one before? Because what if the other one is negative infinity too, so it's positive?
Yeah, so what I would have done is, remember, I plugged in 5 here, and that was headed towards 0. And if I plugged 5 in here, I just get 7. Natural log of 7 is a number. Okay. So I don't have to worry about that. But yes, you would check it, just to make sure.
So why is the reason we're not going to do the other interval, like the limit of r going to from the positive 5?
Okay, because in order to say that an improper integral converges, in order to say that, if you split it into 2, they both have to converge. And what I'm saying is that this one diverges. And so it's impossible for the whole thing to converge. If one piece diverges, then you don't need, then the whole thing diverges.
Okay.
Okay, let's look at another one. These are fun. I'm going to give you a second to look at that. Go refill my drink. I'll be right back. Why don't I give you a few minutes to see if you can't figure out how to set this up? And yeah. I think what I'm going to do is start working the problem out without saying anything. I'm just going to work it, and then you can kind of look up and check and see if you're on the same track. What do y'all think? Anyone have any questions over what I've put up here? Abe, I muted you because we could all hear your phone or something. It was kind of loud for all of us. So just so you know, you're muted.
How did you get in the integration by parts? You got the 1 over x times square root of x, and you got the 1 over square root of x?
Oh yeah, okay, so that is the same as 1 over x times x to the half, which you could look at as x to the half over x to the 1, which is x to the half minus 1, x to the negative half. There's a lot of different ways you could get to that. I like to look at it this way. It's really like square root of x on top and x on the bottom. And I like to think of the bottom as being root x times root x. Root x times root x is x. And then I just cancel one of the root x's.
I see.
I mean, it's different paths, different sorts of algebra, but they should all get you to the same thing. I'm going to give everyone like 1 more minute, then we're going to talk about this because we got a problem. We got a problem in here. Okay, let's discuss this. I'm assuming everyone's good up to the point that I'm at right now. No questions? So when I plug in E, let's see what we get here. 2 times the square root of E. What is natural log of E?
1.
That should just be 1. Okay, so we get 2 root E minus 4 root E, which is just negative 2 root E. Okay, so that's a number, right? Negative 2 times square root of E, whatever that is. Okay, so there's no problems there. Minus, now let's see what's happening here. Here's where we have to take the limit. We're letting t approach 0 from the right. It's very important we're coming in from the right because the first thing we have to do is we have to plug 0 in here for the square root, but you can only take the square root of positive numbers. So it's good that we're coming in from the right or else you couldn't do this limit. But if we replace that t with 0, 2 times the square root of 0 is just 0. So that's headed towards 0, right? Times, now we've done this one several times, right? When we replace that t with something approaching 0, the natural log of that goes to negative infinity. And then minus, this one just goes to 0 again. So we can ignore the minus 0, that doesn't matter. But 0 times negative infinity is an indeterminate form. So that means I've got to go figure out that limit by itself over here. I need to figure out what's the limit as t approaches 0 from the right. I'm just going to look at the piece that was causing the problem. Square root of t times natural log t. I'm not even going to look at the 2. I don't care about the 2. The 2 is there, right? I'm just looking at this piece and saying, what does that go to? Now, we already know it goes to 0 times negative infinity, right? But indeterminate, that means we have to take one of them and drop it to the bottom, right? So I'm going to choose to take the square root to the bottom. And I'm going to do the square root because I think that'll be easier to differentiate. When I move that to the bottom, watch the way I write it. So I realize that square root of t is just t to the half. So if I drop it to the bottom, it's t to the negative half. You'll agree? Now I should have something that I can do L'Hopital on. So I use my L'Hopital's rule here. The derivative of the top is 1 over t. And the derivative of the bottom is -1/2 t to the -3/2. And that equals, let me see, limit t approaches 0 from the right. Let me clean things up here. How do we want to do this? Let's just figure out what all this is. And then the -1/2 on the bottom, I'm just going to put that out front as a -2. Because it's on the bottom as a -1/2, I'm going to flip it up to the top as a -2. But everything I circled in gray there, what does that become?
Is it 1 over t under root t cubed?
I would do it this way. I would rewrite that as that, and then I would bring this one back up next to it as a positive power. And then that's really t to the 3/2 over t to the first power. And that's really just t, you subtract t to the 1/2, which is just square root of t. So it's just -2 square root of t. And now let t go to 0, and your answer is 0. So the moral of the story is this: when you have this indeterminate form, 0 times -infinity, we don't know who wins, okay? Sometimes the 0 wins, sometimes the infinity wins, sometimes neither one of them win, and it's some weird number in between that you don't even think of. That's why we have to do all this work. But here in this case, the 0 wins, so that goes to 0. And then we already had -0. We're not even considering that. So what's our answer?
Converges.
Root e, it converges. This is a convergent integral. It converges to -2 root e. Huh. We get a negative answer. I think that's worth looking at. The function was natural log of x over the square root of x. And we were looking on what interval?
0
0,
to 2.7.
Right, so 0 to less than or equal to e. So we were looking at this function here. That's good enough. And we were looking between there and there. So I've got to bring in my pen here. We were going, here's E. And we were trying to find the area here. And then from 0 to here, we have negative area, don't we? And that area goes down like this. But this area over here was not infinite, but it was negative area because it was below the x-axis. So if you take all of this area right here and you add to it this area, you wind up getting a negative answer. Your answer is negative square root of e. That would be the net area of these two things together. Does that make sense?
So basically, the area below the 0 is negative, but it's not infinite.
It's not infinite though. It's finite.
But it's bigger than the area, the positive area.
That's correct. It's bigger than this area. That's a good way to put it, yes.
Okay.
Okay. All right. Fun stuff. So at this point, you should do your homework for this, which is going to be the same section. You should be able to do all the problems now. All right. I think the thing that's when you look at these improper integrals, the type one are easy to identify because they're going to have infinity in the limits of integration. You're going to have infinity on top or negative infinity on the bottom, or maybe negative infinity on top and bottom. So the type ones are like, oh yeah, this is obviously a type 1, I have to do a limit. The type 2 are the ones that are dangerous because there could be a discontinuity in there that you don't recognize, like the previous example, right? Where you say, oh yeah, this, oh, I didn't even realize that 5 is an issue, right? We have an issue at 5. It just looks like a normal old definite integral. So it's dangerous, right? Danger zone now.
Quick question on that one.
Yep.
So what if it was
What's that?
You got muted, Cameron.
unmuted? Well, okay, instead of x plus 2, what if it was x minus 2? Would you have to do, I guess, 2 more integrals?
Yep.
Yeah, okay.
Yep, you would have to split it into 4 pieces. I'm not going to do that to you, but that's what would happen. Yeah. So let me grab something real quick. 24, 14, exam 2. So remember when we were reviewing for exams, I didn't give you problems like this, but do you see now? Do you see now these problems should have been on the last exam. They weren't because we didn't cover them. But do you see now that this problem right here, you'd have to realize it's a type 1. So you know you're gonna have to break this into 2 integrals, one that goes from negative infinity to 0, and then the other one goes from 0 to infinity. And then you have to actually figure out what the antiderivative of this is. So for that one, you're probably gonna wind up completing the square, because that doesn't look factorable. So you have to complete the square, and then you'd probably need some sort of like trig sub or something. No, if you complete the square, it should go to like formula 17 or formula 19, I think. I would recommend you do that problem. You know, take a quick little, write it down. Both of these problems. This one is a type 1. This one is also a type 1. I didn't give them a type 2 on this one. Interesting. Okay. Maybe I can find another exam that had the type 2 on it. While you're copying those down.
So are these problems from your previous exams?
Yeah, that's from the previous exam. Why is this taking so? Oh, I know why it's taking so long.
So are they like combinations of partial fractions and this topic?
Yep. Yeah, here we go. Here's one. This is an exam from fall 19. This is 1 year ago. So look at this. Look at this one right here. What does that factor to be? Does this denominator factor?
Yeah.
No.
It's -3 times, what is it?
Positive.
Minus 3, x plus
-3, +2.
-3, it's x minus 3.
-3
plus
positive 2.
So if it's x minus 3 plus 2, then the problem you would have is at 3 or at -2, right? But look at your interval. It's from 0 to 1. So would you have a problem?
No.
No.
No, you would not. So you would just do that the normal way. No issues, okay? Make sense? Now you'd still have to do long division first and do all your whatever, you know, partial fraction decomposition on that. This one is a type 1, right? This is type 1 because you see negative infinity there. Look at number 5. Where do we have a problem?
1.
When x is 1. Is 1 in our interval?
Yeah.
Yes. So that's a type 2 improper interval. And then look at number 6. It's an improper type 1, but look at, you've got to do partial fraction decomposition because you have 2 irreducible quadratics on the bottom. So, I mean, this is just, again, to give you a flavor of some stuff I've asked previous classes. All right, can I move on? We good? All right. The train keeps moving, right? All right, we're ready to start chapter 7. Chapter 7 is titled Applications of Integration. So we finally get to do some stuff, some applications. Now, when we say applications, I want to just keep all this in mind. You have to remember this class is focused more towards math people. There are engineering, physics examples and applications that I will try to get to, but we're already behind, so I'm not quite sure how much we're going to get to application-wise. But I'll do my best to do something real world if we can. All right, so we already know that the integral gives us the area underneath the curve, between the curve and the x-axis, right? We already know this. Let me make this a little smaller here. So we already know that the whole idea here was that we started with the function. The traditional integral went from a to b. And then what we did is we came up with these Riemann sums, which was basically all these rectangles. We said the width of the rectangle was dx, right? In the formula, integral a to b, f of x dx. I told you to remember that the dx was the width of the rectangle, right? And the height of the rectangle was just the function's value at some point at the right end of that rectangle, right? So this was our width. I'm sorry, this was our height. And this was our width. Yes? Now, what we want to do is try and figure out if we can find the area between two curves. Instead of the area underneath one curve, the area between two curves. So this is the picture I have here that we're going to take a moment to look at. And let's see if you can follow this. I'll make this a little bit bigger here. Okay, so let's say that we have a function that's a little too big. Let's say that we are given two functions, f and g. We're also told that f is bigger than g on some interval. That means that the f is on top and the g is on the bottom on some given interval a to b. Okay, so f always stays on top of g. So let's say that that's given to us. Then the area between the curves is the integral from a to b of f of x minus g of x dx. Now, that's the formula, but let's understand why. What we're doing here is the f curve, right? The f curve here, that curve, that's the one on top. If we were to find the area between the f curve and the x-axis, the rectangle would come all the way down to the ground, wouldn't it? And that would be f. That would be the integral. That would be the integral from a to b of f of x dx. But that would be all of this area, wouldn't it? Everything here? Okay, that's not what we want. Let me see, I can undo here. Yeah, dx. Now, what about the area just underneath the g? So what if here's the g function, right? Here's g. If we find the integral from a to b, I know that's in yellow, that's hard to see it, g of x, that would be this area right here. So does it make sense that if we want the area that's shaded here in kind of bluish, that we would take the area under f and then subtract the area under g? Just subtract the two? Okay, so that seems logical, it seems reasonable, but that's not quite the way I want you to look at it. I mean, make sure you understand that, but look at this picture I drew to the side. I know that this looks complicated and you may be sitting there going, what? Trust me, this is going to help us in 7.2. So here's the way we're looking at it. We have, let me copy this. I want to take this into a place where I can use different colors. Okay, so if we want to know the area between F and G, we again can imagine cutting it into a bunch of rectangles. Now, if we can figure out a formula for one of the rectangles, then we can just add them all up by using the integral, right? The integral gives us a limit of a sum. So it allows us to create an infinite number of these rectangles. I just need a formula that represents the area of that thing. So what I do is I try and figure out like how tall it is and how wide it is. Well, the width of this thing, right? The width of this is still dx. It's what it was before. Now I highlighted that up here. The width is still dx. It's the same thing that it was when we were just dealing with a single function. The difference is the actual height of this rectangle. So the way that I get it is I say, all right, well, how big is that piece on top? That piece all the way to the ground, right? All the way down would be F, and that's what I have here in blue. And then the distance from the bottom of the rectangle to the ground, that's G. That's what I have there. And so if I wanted to know the actual rectangle's height, like that height, I just take the F and I subtract the G. Does that make sense?
So you're basically just doing height minus height.
Height minus height, exactly. The top one minus the bottom one. Yes?
Yes, I think it does. My question is, so even if we do the same thing, we get the height and the width of it. Well, is there a formula so that we can get rid of the excess space that's left?
What extra space?
Like, you know how once you introduced us about this idea of putting in triangles or squares, there was excess area that wasn't covered by the triangles, or
it's already removed. It's removed when you do the integral. The integral gives you the limit of the sum, so it creates an infinite number of rectangles. So you have no error. And then the fundamental theorem of calculus allows us to actually get an answer. Okay. So there is no error in this computation at all. We look at the visual of what's happening to create the formula. So this right here, the area of one slice, look, the area of one slice, okay, the area of one slice is that blue formula right there. That's the area of just one of those rectangles. It's this piece right here, which is the height of the rectangle, which is that piece right there. And then this dx is the width. That would give me the area of one slice. I want to add up an infinite number of them. So what I do is I just throw the integral sign in front of this, a to b, and that gives me the infinite number of them added up. Okay. That's the whole beauty of the whole integral idea, is that it allows us to add up an infinite number of things. What you're going to see very soon as we proceed here is that when you do an integral from a to b, what's in here so far has represented area of something, but it doesn't have to be. You can add up a lot of things. Like anything you want to add up an infinite number of them, whatever it is, you can do that. So if I later on have a formula like this one in blue here, if I have a formula that gives me the volume of something, then I can use the integral to add up an infinite number of those things and get a total volume. The integral is arbitrary. It doesn't care what you're adding up. It's an operator. No, it's an operator. It's not called a function. It's an operator because operators take functions in and spit functions out. So it's this thing that we can use to operate on functions. All right, I'm getting ahead of myself. All right. Okay, so let's see if we can do an example. That's the formula. Yeah, I'm skip that for a second. So let's do this one right here. Sketch the region bounded by y equals 2 minus x squared and y equals negative x, and find the area of the region. All right, so this is where we're gonna take this thing off our desks, get the dust off of it, and you might need it to graph. Now, it's gonna depend on you, all right? But these two functions here, everyone here should feel comfortable graphing. I'm gonna sketch them first, okay? So let me start out by drawing an x, y axis. I'm gonna try and make this pretty big. Okay, first one, let's do the first one in blue. 2 minus x squared, that's a parabola. It opens down because there's a negative in front of x squared. The 2 up front means we move it up 2. So if I go up 2, I draw a dot, and then my parabola opens down. I'm gonna be pretty relaxed about how I draw this. Here's my parabola. That's y equals 2 minus x squared. Now the other one is going to be y equals negative x. I'm gonna do that one in red. Y equals negative x is, well, y equals x is the diagonal, which we call the identity function. This is just that with a slope of -1, so it should look like this. That's y equals x. Now, is it clear to everyone what the region bounded by these two is? Does everyone see it? It's this region right here. Okay, it's that region. We want to know the area of that. Now, do you all understand that you cannot say that it's over here? That's not the region bounded? Because this continues to open up forever, right? It's not, that region is not contained. Only the region in yellow is contained. Even if you said down here, that's not contained because they keep going down forever. So that is the only region that we could possibly be talking about here. So when you look at this, is it obvious to you which function is on top and which one is on bottom?
Yes.
Yes, right? So if I needed to, I could label this one as my f of x. In other words, this is my top function. And then this one right here, this one I can label this g of x. Oh, that should have been a negative on that, sorry. And that's the bottom function. And I already know that the formula for this is going to be the top function. So it's the integral of the top function, f of x. I forgot the squared there too. The top function minus the bottom function. Okay, that's the formula. It's the top one minus the bottom one. But I still need what here?
The limits.
The limits of integration. And those are your x values, aren't they? Those are where these two graphs hit one another. It's that point, and it's that point. And how are we going to find those?
We set x equals to y.
We set
Y equals to x.
We set the functions equal to one another. We want to know where these two graphs hit each other, right? So we set them equal to one another. So I'm going to do that up here. I need to find
like solving them simultaneously.
You could say that. Intersection of those two would be setting the two functions equal to one another. So I'm setting the f function equal to the g function. And solve that equation, which happens to be a quadratic equation in this case. So I'll just move everything over to the, let's move everything to the right side. And fortunately for us, the right side factors. If it didn't factor, I'd have to use a quadratic formula. But we get two nice solutions, 2 and -1. And those are my limits of integration. Questions? Just got rid of the minus, turned it to a plus, dropped some of the parentheses there. And that's it, right? This should give us the area between these two curves. Now, am I actually going to go compute that right now? No. This is a simple integral, right? This is very easy antiderivative here. Very easy to take the antiderivative, very easy to plug in the numbers. You get a numerical answer. That's for you to do, not me. I'm not doing that anymore. So I'm stopping when I get to points like this now, all right? On your tests, I will have you calculate a few of these by hand. Take them all the way to the answer, but a majority of the next test is going to be, give me this, move on to the next problem. That's what a majority of the next test, because we don't have time to do computation. We know how to find antiderivatives now. It's can we convert the problem into the math? The math we can do. It's can we turn the problem into the math? Understand? Okay, let's look at another one. Square root of x. Okay, so let me grab this example. Sketch the region bounded by these two functions. Or sorry, by all of these. So we got to be careful here. Notice that they gave us 3 things. Okay, y equals the square root of x. I'm going to do that in blue. Yes, you need to know what that looks like. Okay, the next one I'm doing red. This is y equals x minus 2. That is a line, has a slope of 1, has a y-intercept of -2. Something like that. So right now, is there a region bounded by those two? No, there is not. You might think it's right here, but it's not, because you see that this is not closed off right there? See that little green part's not closed off? But look at the last curve. The last curve is y equals 0. What's y equals 0?
Straight line.
Which one?
The y-axis.
The
the y-axis.
Y equals 0 is the x-axis.
Yeah.
So y equals 0 is this one right here. See that? Got that? That's y equals 0. So now do we have a region?
Yes.
Yes, the region is this right here. Now the tricky part. Let's see. Does anyone see why this is going to be a little tricky?
There's more than 2, I guess, functions.
The area.
There's more than 2. So think about the rectangles right now. Okay, I'm going to zoom in on this. Think about our rectangles. Our rectangles look like this. And there's an infinite number of them in here, aren't there? What is the difference between that rectangle and the rectangle over here? What's the difference?
The height.
Okay, the heights are different, but in terms of the formula for its height, what's different about the two?
Also, like, remember you showed us in the first part that there's a space in between the x-axis and the y equals the red line. So we need to compute for that too. Like we need to subtract the overall height with the one that it's in the shaded area.
Yes, but I'm trying to, let me write this down. The general idea is this. If we're going to do the area between two curves, we basically have to figure out what the top one is and what the bottom one is, subtract the two, and then, yeah, we'll have limits of integration. We'll have to figure that out, and, dx or whatever the variable is. But it's basically top minus bottom, right? Look at this first rectangle. What's the top function?
Y, the blue one.
The blue one, square root of x. What's the bottom function?
Oh, the purple one.
The purple one. But this rectangle, it's different. The top is the blue, but the bottom is the red.
Can we add the bottoms then?
Pardon?
Couldn't we add the bottoms then?
What do you mean add the bottoms?
Like, because they're both the bottom function no matter what. The top would be y equals square root of x, but the bottom would be y equals 0 plus the linear equation.
Okay, yes, almost. We
but
are
what
going,
about we separate them?
What?
Like separate them into two integrals, like for example.
We're going to separate it, exactly. We're going to split it. We're going to see that there's a natural point here at which if we split this into two integrals, the first one going from here to here, then the top and the bottom are always the same within that little region. And then a separate integral that goes from here to whatever this point is, where the top and bottom are the same. Does that make sense? I think it's obvious that this left point is 0, yes?
Mm-hmm.
So we're going to do two separate integrals. We're going to do one, let's say is going to be this bluish one. Bluish, it's now green. And then we'll do this purplish one, yeah, which is now red. Okay, it's two different integrals, yes? All right, that's a lot of crap up here, but let's see. What are some things that we're going to need to know? Well, we're going to need to know those question marks, aren't we? Let's see if we can't get the two integrals, though. The first integral and the second integral.
Can we get them when we're getting the limits? Can we just do it, separately?
Yeah, we will. Can you tell me on the first integral, which is going to go with the green one, what the top function is? Again, y'all said it was what?
The blue one.
Under root x.
So square root of x, and then minus, what's the bottom function?
0.
Which is 0. So that's just that, right? And then the other integral, the top function is the square root of x, but the bottom function is actually not 0. It is, isn't it the x minus 2? Now I need that in parentheses, right? This is the top one minus the bottom one, and that negative will distribute through. This making sense?
Yes.
Okay, now let's get our limits of integration. We know that this first one is 0. Okay, that's obvious, I hope. What about the second one? Do we know where that point is right there?
2.
It's 2. Now you know that because that's where the red one hits the x-axis, right? In other words, that's where the red one, which is y equals x minus 2, that's where that one hits the purple one, right? So if you set those two equal to one another, right, you get x is 2. So we know that that's 2. And that means this other one's going to start at 2. And now we need to find the last point, which is going to be where the red and the blue intersect, which means you have to set those two equal to one another, right? So I'm going to do that. That one I'm going to have to work through. Intersection I need to set the square root of x equal to x minus 2. Does everyone understand at this intersection point, there really wasn't a lot to do because it just so happened to be the x-intercept of the red one. So there was really no work to be done other than just identifying, like, plug in 2 and you get 0. Is that all right? But on this last intersection point, we actually need to do the algebra here. How do we solve that equation? What type of equation is that? You know what that's called? It's not a quadratic. What is it called? No? Square root equation or radical equation? So there's like a whole set of steps on how to solve a square root equation. The first step is to isolate the square root by itself on one side of the equation, which we already have. The next step is to square both sides of the equation. So we square the left and we square the right. When we square the left, we get x. When we square the right, we have to actually square that and we get that. Also, I'll remind you that when you do square root equations and you square both sides, you at that point introduce the possibility of what we call extraneous solutions. So we will have to check both, like whatever answers we get, we will have to check them to see if they do actually work into the original equation. But let's solve it first. We can now move the x over, subtract x on both sides. And then fortunately for us, that now factors. And we have 2 potential solutions, 4 and 1. So we have to check though. We have to check into the original equation, which is this. Let's check, does 4 work?
Yes.
Square root of 4 is 2, and then 4 minus 2 is 2, so that works. Does 1 work? Square root of 1 is 1. 1 minus 2 is -1. That doesn't work. That's an extraneous solution. So that means that we intersect at 4.
It's what again? What kind of solution?
Extraneous.
Extraneous.
Extraneous solution. But we can say now that this is 4, so that integral goes to 4. Now, can you handle those 2 integrals? I think everyone here can take the antiderivative of the square root of x and then plug in 2 and 0. And I think everyone can handle distributing the negative and doing these each individually and plugging in 4, plugging in 2 and getting a numerical answer. Yeah? Okay. That's all we can do for today, or that's all we're going to do for today. Make sure you finish the 6.6 homework. We'll come back. We'll do more of this 7.1. We still
I have a question here.
More to talk about here. Yes?
Why aren't we using the 1 here?
Because one is a solution that doesn't work. If we plug 1 into this right here, it doesn't work. Plug 1 in. Square root of 1 equals 1 minus 2. Square root of 1 is 1. 1 minus 2 is -1. Those aren't the same.
Okay, so we need them to be same. Okay.
Yep, that's what I was saying. You're always allowed, when you're solving equations, you are always allowed to square both sides of an equation. You can always do that. However, you may have created answers that won't work. Okay, I can give you the most basic is if you got to go, y'all can go. But let me just tell you, what if I tell you this? X is equal to 2 or -2. Okay, everyone, X is equal to -2. Now, you decide to come in here and square it. I would agree with you that x squared is 4. I agree. Now, try and go back to x. So you would take the square root on both sides. Whenever you take the square root, you have to do plus or minus. So now you're saying that x is plus or minus 2.
Yes.
Well, it's not. I told you x was -2. Now you're telling me it's both plus and minus. Well, it can't be. You know, so that's what we're doing here. When we square both sides, that forces us to check our answers.
Okay, understood. And why is there a 0 on the radical? Yeah, here. No, not here. The limit 2 over 0. Yeah, this limit 2, 0. Yeah.
Why is this 0?
Uh-huh.
Because that's our first point for this region.
Okay, 0 to 2.
Yeah, and now we didn't solve that, but we just did that just by visualizing it. Went from 0 to 2.
How can we solve for a 0? By
You would have to figure out where this blue curve hits the purple one.
Oh,
so
okay.
you'd be setting these two equal to one another, square root of x equals 0. And the only possible solution there is 0 itself.
0. Yeah. Okay, thank you.
Yep. Anything else?
Could you technically like if you wanted to solve for a